We now move on to the second technical presentation for the day, and the speaker is none other than Sri Arun Kumar Bhatia. Although he needs no introduction, but just to formally introduce him to the audience, a few lines about him. Sir is a consultant, facilitator, and trainer. From the last 17 years, he is based in UAE with exposure to Middle East, North Africa, Indian subcontinent, and EU region. He gained experience in diverse faculties, including project design, project management, product application, and project sales, while working with international groups like Maikawa Japan, GEA Germany, and Gunter Germany. He is also a board member for Ammonia Association of India, that is AAR, and fellow member and follower of international associations, including ASHRAE, IIAR, and TMI from USA. Sir is going to be talking today on a very interesting topic, that is energy efficiency through improved air distribution using CFD analysis. Welcome, sir. The stage is all set and yours.
Thank you very much. Thank you, Ishre. Thank you, Nuremberg Messe, REFCOLD India, and entire team working in refrigeration and cold chain industry. So today's topic, which I've been given responsibility, related to air movement. So the topic is energy efficiency through improved air distribution using CFD analysis. CFD analysis, I think it is still upcoming subject. It is still a new thing for cold chain industry, especially in our part of the world where we are currently residing. But Europe, it is popular from long time. Now the topics I will talk today is that are divided in, first of all, we talk basic, which is refrigeration, and then we talk about air management, which is related to the topic. Then we come to our core subject, which is CFD, which is computational fluid dynamics. And then we go ahead with a few case studies just to explain whatever we have gone through. And then there'll be a question and answers. So let us start the presentation. So normal vapor compression refrigeration system, we have a condenser, we have a compressor, we have a evaporator, and we have an expansion valve. And if I have to given a choice, and if I have to analyze system, so this is the way the energy is consumed, or I must say the stakeholders in energy consumptions. So compressors, of course, they will consume most of the energy, and then coil are the most important part of any cold chain or food chain application where air coolers or air cooling coils consume lot of energy. So today our focus will be to understand how we can reduce or how we can optimize or how we can help people understanding that there is a possibility, there is a scope for us to save energy. Now this is very much related to air management. So if we are able to manage air properly inside the chamber, definitely we can save a lot of energy. So air, as I remember, one of my mentor in Netherlands, he used to tell me air is very stupid. So you just blow air, so it will go wherever it find the pass. So let us see how air behave in a chamber and how we can get to know the energy saving techniques using air management. So the game we are getting into is energy saving, and we have very limited scope where we have airflow, air throw, cooling capacity, air temperature, and who are our opponents. The opponents inside the chamber are tracking system, the packing of the product, the size of the product, size of the store, material to be stored, and the temperatures. I think the air evaporators or air coolers or AHUs or whatever you say, there is a tremendous scope to get energy savings here. And these energy savings can be achieved by a few simple things. Let us go ahead and understand how we can save this energy. So what air does in a cold store, or what air does in a cold chamber? It goes with the speed, which we call velocity. It goes with the volume, we say flow, and it carries a temperature. So basically, three properties which are the most important are velocity of air, temperature of air, and flow of air. So these are three important parameters or properties which we have to analyze, and this will help us to define how much energy savings can be done. Now, what I have been understanding and what I have been felt and what I did from many research and from my mentors and the cold stores we have done, that we can achieve about double digit savings, which can go up to 15, 16, 17% if we do our air management in optimized manner. So let us go ahead and see and learn. Now, this is the air volume which industry follow or recommend, or this is the optimum in volumes of air inside any chamber. For example, if we are storing the frozen products inside a chamber, the air circulation volume will be different. So what is air circulation? I think it is mentioned here at the bottom, which most of our industry engineers, consultants, or young talent contractors, they know about it. And if we are blast freezing the product, then air volume should be higher. And if we are shock chilling the product, shock chilling can be for a meat industry, can be for a pre-cooling of fruits and vegetables. So like that, there are different air volumes we are going to use in different applications and chamber sizes. Now the second important point comes is air throw. So air throw is, if we go and understand the name air throw, so logically we understand that it is how much air we can throw. So understanding here is, if I am putting evaporators or air cooler at one side of the room, the end of the room should be covered. So what I am trying to say, if I am producing -10, -5, or -20 or -30 °C of air at the exit of evaporator or air cooler, it should be able to reach at the end of the room. So my product which is stored at the end of the room should not face any hunger in terms of temperature management. So the product which is stored in front rows can get the same equal treatment in terms of temperature management, which is very important and essential to maintain the quality of the product. Now evaporators, in standard evaporators, we use two type of evaporators. One is blowing downwards and another is blowing horizontally. So the case studies which I will take, they are also related to these two kind of evaporators. One is going horizontal flow of air, another is vertical flow of air. And the next important point is the temperature management inside the cold room or in the chambers. So temperature management, what I can understand from this, if I am producing X temperature of air, it should reach to entire room, and this must return to the air cooler. If the air is not reaching properly back to air cooler, then also there is a lot of efficiency management on the stake. So we have to also make sure that whatever air we are generating of X volume and Y degree Celsius, it should come back with a proper flow. So here I have shown you an example. For example, minus 31 degrees Celsius, air is given to a product and air is coming downwards. And it is returning back at minus 29.7 degrees Celsius. So this is just an hypothetical figure. The air return temperature depends upon the refrigerant and so many other factors in the product temperature even. So air is automatically coming back and it is going above for a suction. The phenomena which we call is a chimney effect, which I think most of our industry colleagues, they know about it. And this is another example of air blown downwards. Now here comes our main topic of today, which we call computational fluid dynamics or CFD. As I remember, I came across these terms, I think 10 years back, when we used to visit for a lot of training and brainstorming sessions. And then I was amazed to see how companies in Europe were using this method to create efficiencies because the energy costs were started rising there. And the challenge was how a contractor or a manufacturer or engineer, consultant, or any other stakeholder in food chain or cold chain can help reduce energy consumption in cold stores. So then this computational fluid dynamics came in action, or rather, I personally came across this term. So what is CFD? The first question comes to our mind or my mind. So it is nothing but if you go to developed countries, there is a driving test. So they are done virtually, right? There is a simulation. So it is same way. What we are trying to do here is from some equations for. I mean, if we go ahead and study these equations, this will be entire big sessions, and I'm not master for that. Like Navier-Stokes equations, turbulence modeling, which depends on Reynolds numbers, and there are some other modeling techniques where we go ahead and learn and achieve what is CFD. Now, the first step in computational fluid dynamics or CFD, now onwards, I will only use shorter name CFD. We have a data for a cold store or we have a data for a chamber. Now, every chamber we design or every racking system we put or any product we put inside, there is always a CAD drawing we start with. As a contractor or as an engineer or as a consultant, we start with a drawing. So CFD is also simple. So you create, the first step is to create a drawing, which can be a CAD.data or any other form of drawing. Then that drawing is divided into certain mesh or matrix or certain area where a lot of points can be used as a reference. So we call technical terms are there. We divide this area, and these small parts are in an area are defined in a boundaries, and we can domain this as a tags. For example, if I put a triangle here in the chamber, these are the boxes. So understand in a way that this is a blast freezer or this is a cold room, and product stored in X square having different temperature airflow. product stored at the extreme end of this chamber in a Y block. So this we are just trying to do to understand that in a particular area or a particular space, how much temperature, how much airflow, and how much other parameters can be found, and those parameters can be analyzed to achieve our goal. And this information, these parameters can be fed into a software which we call CFD solver or CFD simulator, and then we get the desired result, and from the desired result we get our study done, and we go ahead making our design analysis. Now let's go ahead. What is next? Now, how CFD can be beneficial for us in a cold chain? There are many things which we don't analyze on daily basis. For example, racking arrangement, packaging design, ESP optimization. ESP is a very important factor for evaporators and fans, which help us to understand the power consumption of a fan motor. Or rather, higher the ESP, we have to put stronger motor, which means a higher kilowatt. So if higher kilowatt, it means we are consuming more power. Airflow optimization, yes, we have already talked about it. If we have less airflow or less air volumes, we cannot achieve our cooling results, we cannot achieve our product quality, we cannot achieve the desired result which are required for a healthy and a nutritious product. Indeed, the next important point is chamber's geometry. Chamber geometry, yes, it plays important role, because if your chamber is a larger chamber, for example, I have seen evaporators, the chambers are long, the length of the chamber is like 100-meter long, which for our country like India or Indian subcontinent, so 100-meter long chamber, personally I have not seen. And the height of the chamber 30 to 40 meters, which definitely a challenge for us to understand how much we do air optimization inside the chamber. So chamber geometry is very important for air temperature optimization. So the main objective, we may conclude that CFD is a simulation to remove traditional barriers to analyze better design and achieve double-digit energy savings. For what? So what is CFD? Which means we just trying to do a simulation just before the project to be done, or just before the projects to be installed. So it helps for us to design optimization or anything which can help us to foresee the future of our chamber and help us to optimize the performance. But here we are only talking about air distribution and air management using CFD. So here I have given some thermographic images which I have received from some of the reputed manufacturers from Europe, and I have acknowledged them in last of my slide. I cannot say the names because that is. Now here if you can see, there are the color wise you can see temperature from bottom to top. Darker blue is a extreme range of temperature, -27, and the red is -20. So the parameters you can always put in CFD simulation software. The color settings, the parameters you can always put. For example, in this case, the simulation engineer have considered -27 for dark blue and -20 for extreme red. So this can be changed also. So first slide, I missed to mention that evaporators are placed at 3 sidewise blowing in a chamber. And the second we see the effect here. The third, the temperature distribution can be analyzed if evaporator is on the side wall of the chamber. And similarly, velocity streamlines. For example, here we can see how the air is blown and seen at the end of the chamber. And below right, you may witness velocity distribution in meter per second and the chamber temperature profile also. So now let us move to our case study 1, where we will understand a chamber of approximately 80 meter length and 40 meter width and 25 meter height. So this was a project where a manufacturer and a consultant and the owner, they have already finalized an order with a reputed manufacturer in Europe. Okay. Now they wanted to make sure the evaporator selection, what they have done, is it okay? Or is there any chances to improve? Or is there any chances that they can optimize airflow management or temperature distribution management? Or we can have enhancement in thermodynamic performance of evaporators. I hope you remember previous slides where we mentioned that we can achieve double-digit energy savings if we are having a good and efficient air distribution in the chamber. Now, the one thing you have observed that this chamber is a long chamber. So if it is a small chamber, 10 meter, 5 meter, maybe stakeholders like owner or consultant may not bother about going ahead with CFD simulation. But this is a very large chamber and they wanted to make sure that the result should be achieved. Now this is the first thing they have done as a simulator. They try to place evaporator on one side of the room. Here you can witness the air is blown from an evaporator and this is going till the last end of the room. So we can visualize that I think most of the chamber is covered with the air. But another important point which you can understand is Quanda effect. See, Quanda effect is, I don't want to explain that most of our engineers, they are aware, but it says that whenever some fluid it is flowing, so it has a natural tendency to go towards the extreme end, towards the walls. So if you see here, the airflow is going towards the wall of the chamber, the top, the roof of the chamber. But important thing you must understand on right hand side figure that the middle of the room, there is no air, or as an engineer, I can analyze that the product stored there will be always staying hungry and the product will not be able to get the temperature which it want. So which means the product store here may not be a good quality, may not be as per the standards required for nutritional value, or it may be spoiled product. Now the second simulation done in this case was where two evaporators are clearly visible. So you can see in this simulation which I have received, the air is not able to reach to the end of opposite end of the room. So we have a challenge here that the product which is stored at extreme end of the room, the product is not getting enough air, which means product may get spoiled. So what we should do next? We should have high capacity fans, which means high capacity motors, or we try to change the speed of the fan. There are various options available, but it is a prerogative of a designer, because the designer knows what evaporators and what conditions is actually existing at the site. Or a simulation software can only define the parameters which we put inside the software. Now this is another top view where we have done air distribution study with the X type of evaporators. So here you can see the air is not reaching at the end of chamber. Yes, I think we remember from previous slide that the chambers are long. The chambers are close to 80-85 meters, and there are a lot of resistance in between. There are product, there is a racking system. So the fans are not able to push the air to the end of the chamber. Now, if we go change the fan specifications, still, if you go at the bottom, if we are going to, if we are increasing the velocity by changing speed or other measures, then we can observe in a bottom, there is a zones. If you see these lighter color zones, so these zones, you can see there is no enough temperature management. When I say temperature management, so we are not able to manage the temperature of the product which is lying on the racks. Okay. For example, if I have stored ice cream at -25 and the manufacturer specification is the stored temperature should be -22 plus minus 1 degree or -24 plus minus 1 degree. So I cannot go below certain recommended temperatures, because this, if that particular product or ice cream go below certain temperature range, it may lose its properties, which means losing a taste in a layman understanding, and in a food technologist understanding, that it loses its structure, which is healthy and nutritional value. So what designer will do? Designer have studied that these evaporators or different simulations with higher airflow, lower airflow, extreme velocity, he is not able to do the justice to the chamber. So then he does another, the same test. He has seen the velocity streamlines. Here also we can observe the same way. The first slide they have shown that there is a lot of places where temperature is not maintained. So now in this case study we can understand that we can create a correlation of air throw and air volume and air temperature. So what designer have done in this case, designers have concluded that it is always better to put two evaporators at two different extremes. For example, two evaporators on this side, left hand side of the chamber, and two evaporators on the right hand side of the chamber. So that was the best solution we could achieve on this particular case, as that was commercially viable, and it was also a lot of energy savings in that case. And the positioning of evaporators were decided agreeable by evaporator manufacturer, the consultant, and the owner. So see, by simple study, we are able to find out what are the best suitable evaporator. Now the question comes to my mind, why we don't do this in normal chambers? I think because the smaller chambers, there is no challenge sending air or air volume maintenance. So larger chambers, this is a real challenge. So in this, the case study one, we can conclude that the placement of evaporators can be studied by using the CFD analysis, and by this we should we are able to achieve our desired results, which is ultimately it's the game of power saving, and we have to be responsible. Now let's move ahead with the another case study. This is the case study which was done by an university. I have already acknowledged their names. So in this case, we are going to study the simulation of air and temperature inside a pre-cooling chamber. And here we are not only going to study the air management or temperature management, but the most important thing is how a product is able to get enough air to stay in a desired thermodynamic, thermodynamically healthy. So in this study, we had there was a simulation done for a pomegranate cooling. The pomegranate pre-cooling requires a temperature, airflow, and an evaporator placement. So this study, we had certain type of boxes. In these boxes, we have done careful study previously that the air should flow inside these boxes, cooling pomegranates, and these boxes can be modified. These boxes can be redesigned to help a temperature management and airflow management. Now here you can see these boxes are stacked in different ways. There are bottom left, front right, bottom right. So the air is forced through these boxes. So there are two arrangements which we have done. There are 7 layers of 10 boxes. There are 10 and CT2 boxes, 8 layers of 12 boxes. And each carton is packed with 12 pomegranates. The weight was approximately 4 kg. And then we went ahead. And what we found was very interesting, that CT2 type of packaging, okay, has a lowest pressure loss. See, pressure is very important for air management. In this case, the design of the box, a particular design of the box, which we'll also see in next slide, there was a higher pressure resistance. So if I am pushing air through the boxes and it is taking a lot of effort and the air is taking a lot of power, which means I have to put a higher capacity fan. So X evaporator can come with a 5 kilowatt fan, or it can come with a 7 kilowatt fan. So you see, my design of a box or my design of a racking arrangement can increase or decrease maybe 20% of a power consumption for a fan. So this was the only objective, to study this type of packaging design. So if you go ahead in the graph, you can see the CT2 has highest loss, which means they have to use very high capacity fan, or they have to use a higher capacity fan to achieve same result, which in case of CT2 without lining. Now this was the CFD which was done. So if you can observe, there was a velocity with, if you see in blue case, we have put a 0 for same way like we put in PLC sensor setting parameter 0 to 0 is the lower limit, and whatever highest limit we can set. So 0 to 5 meter per second velocity, which was the target for forced air cooling. The air is pushed from left hand side, and it is going to exit from the other end, resulting pre-cooling of pomegranate and helping pomegranate to stay longer life in a cold storage or a cold chain. If this was done at a post-harvesting site, which means closer to the farm, and this is very necessary for food chain, cold chain, or food security. Now, in the second box, box B, we can see there are smooth temperature. The force air is going through it, but you can see the cooling on the extreme end of the box is not visible, or I can at least see the lines of a temperature or line of air. The stream, it is not a very streamline, and these are not well channeled, which means the power consumption we are using to generate colder air is not, the cold is not transferred to the food, and it must be transferred to the food because we are consuming power to generate air at a temperature, and by that, if the air is not reaching properly, which means we are consuming higher power and we are not getting results. And what is our objective? Our objective is to have best airflow management, temperature management, to ensure that our food or our fruit pre-cooling is done in a most efficient manner. Now, modification of vent holes. These were the holes which were inside the carton box. If we go back to this slide, if you see, there are different arrangement of holes here, and here the carton B is a different arrangement of holes. So now we have done some modification in both container 1, which is A, container 2, which is CT2. And doing this hole or a temperature management, we have redesigned now container 1. Now you see there was a model and there is a B, which we have done certain modification. Now the round is changed into the vertical ones, just to understand and just to make sure that air management can be maintained properly, and resulting that we can save power. And see, we found interesting results. Now, if you see here, redesigning the CT1 box, the redesigning the box help us doing wonders. And here I was even surprised because I have not personally, I was not aware that even CT, even simulation done with the packaging can help us to save that much power. Yes. And now you can see in a picture A or a simulation A, some products are not able to get enough air. That was due to the boxes which were not properly designed. In a redesigned box, you can see there is enough cooling on each product. Which was the product? It was pomegranate. And we are able to achieve enough air cooling. And these two results, what I'm trying to tell is these two results are not concluded very easily. There are the simulator, the engineer had to do a lot of simulations to reach to this level and to conclude what is the most efficient manner that we are pushing air at 7 degrees Celsius, and that air should be transferred to a product which is pomegranate in this case. For example, there are products like grapes in India. So the grapes pre-cooling is also very challenging. There are many people, they have done research, they have done a lot of things in India, but again, CFD can be one of important technique, or it can be one of important engineering method which can help us to analyze existing chambers, and also it will help us to for our future products, because pre-cooling, the stakes are very high, the product cost is very high, and if we can save energy using same amount of energy or using less amount of energy and getting better results. The point here is to get better results. Now, what was the conclusion from this case study? The conclusion drawn was the pressure losses and airflow patterns and temperature distribution can be achieved by force cooling of pomegranate in an efficient manner if you use CFD in a proper way. Now, the pomegranate was packed with a lining. A lining, I must say, the lining, it is kind of a polythene wrapping done on a product just to make sure when we are force cooling the product, there is a moisture which can be escaping from the product. Yes, I think most of the refrigeration engineers and designers, they understand this phenomena. Because of temperature difference, the moisture will be escaping the surface of the fruit. So this, to avoid that, the farmers were using the lining, which was a polythene lining. So that the way they were using the lining, there were a lot of velocity losses, and the temperature and airflow management was not able to use properly. So our external static pressure or a pressure on the air was so high that we were consuming more power. So by CFD simulations, we have highlighted or we understood that it is essential and it is the most important that we must understand that design of packaging is very important in airflow management. Even smaller details like plastic lining, packaging, crate arrangement is essential, and it is a key parameter which can help us to reduce power consumption. So don't forget, we are using same evaporator, we are using same fans, but we are now getting higher effect of air transfer or a cooling transfer to the product. How? Because we are able to study or simulate the performance through CFD. Now, this case study also highlighted that force cooling of pomegranate fruit is essential at post harvesting site. But how we can make this power efficient, how we can make this energy efficient, that we can reduce significant load on the fans by changing package design, by changing airflow management, by modification of lining or modification of packing. I think with that, I will end, and I am at the 41 minute of my presentation. I think that was the time allocated to me. So I will hand over to the for the question answer, because I would like to take more question answers. Yes, over to you for question answers.
Which type of facility is CFD most essential for?
I think this is the question which I always ask myself, and there is a thin line. But I personally believe the store which is like a big chambers, stores which having larger areas, the stores which, for example, the store which we studied in a case study one was 80-meter long. So airflow, air throw, air volume, temperature management was a challenge. So if I'm the owner, if I'm the consultant, I will definitely go for a simulation, CFD simulation for these kind of store. So my answer to this is that store with the larger areas, larger areas in length, width, and height, we must try to go for CFD simulation. This is first part. Second, also, wherever we have a high value product and power consumption is very high. For example, pre-cooling rooms, there are a lot of products and the pre-coolings or blast freezing in done in a shorter period of time. And the power consumption there is very high, and it is a money-making machines. and it is there we consume very high power. And I would recommend high bay cold stores, which is high height, longer lengths, and also pre-cooling rooms and blast freezer rooms. So I hope I am able to answer.
How difficult is it to set up an efficient CFD infrastructure with lab professionals, etc.?
See, CFD is very much relevant to our country, as I always believe that Indian brains are one of the best brains in the world. And I'm really proud that I'm an Indian and I owe whatever I learned to India. So my country is very special, and the project what we are doing is also very special, and we are always willing to take risk and doing new techniques in our cold chain industry. In our countries, there is a lot of projects which are happening. For example, fisheries segment where blast freezing is done. We can do some analysis on that. We can check how CFD simulation can help us save power. Because till date, we are only believing on certain manufacturers. We don't know how the result of a particular evaporator will be transformed, or rather it will help us to get a desired result which is promised. A pre-cooling room, for example, a state like Maharashtra, where a lot of grape pre-cooling is done. There are other states where a lot of pre-coolings of other fruits and vegetables is done. So there we can do some simulations, but we have many research fellows in IITs and other institutions. There are many papers available on internet. So answering your question, there are a lot of scope in our countries to use in existing projects and future projects.
The second question that I can see on the chat box is, can we use thermography as a validation for CFD design?
I mean, I'm trying to understand, but whatever my knowledge is, see, CFD, as I always believe that we have one of the best brains, particular in terms of Indian context. India have got best technical brains. So setting up a lab or setting up any simulation mechanism is not at all difficult, because there are challenges. People say there are challenges about intelligence, or there are challenges about intellectual things, but that point is already I will not consider in terms of India. But yes, there is a lot of cost involved with it. I think we are best software engineers. I think we should encourage, or we should have some simulation software designers in India. And as a industry, or as a ISRE is a very positive organization, so ISRE can take this step and help. Maybe they can help. They can take this mission further, setting up some software engineers, young students. But currently, there are some simulation softwares, they are available, but they are highly expensive. For example, as far as I know, they are costing around 40 to 60,000 euros, which I think this is not justifiable. We are here trying to improve farmers' life. We are not here to spend so much money. Our country need improvement with the least investment. So my thinking is the cost is very high. If you go with a European or American simulation software, this is as per my knowledge. Yes, there are some software companies which are claiming that they can do some software which is available on cloud, and this cloud software and cloud mechanism is another point which is upcoming, and it can definitely help us getting, this thing makes accessible and easily available to everybody. And coming back to your question, I think it is very easy to set up an infrastructure. It is very easy to set up a software, but currently these softwares not economically, for me, they are not economically viable.
Thank you, sir, for that wonderful presentation. And I see we have got very good participation from the audience, and there are quite a few questions in the chat box. In the interest of time, I would like to take up a few. So, sir, the first question that we have for you is, how difficult is it to set up an efficient CFD infrastructure with lab professionals, etc.?